Just before human babies are born, the brains are not fully formed. They can handle all of the basic functions, but they're just getting primed and ready for the main show. All of the new input that will be received by the five senses outside of the womb after birth. Once babies are here, their little brains are like solid sponges, ready to soak up everything they encounter. But they don't just take and store all the information they get. They start to form neural pathways for all of that input that will stay etched in place for life. These pathways, or maps, are the subject of the book Brainscapes, the warped, wondrous maps written in your brain and how they guide you, written by neuroscientist Dr. Schwarzlose. She holds a Ph.D. from MIT, is a researcher at Washington University in St. Louis, and the past chief editor of the journal Trends in Cognitive Science. We'll speak with the doctor about how our brain maps represent how we experience the world in this one-on-one conversation into the human mind. I'd like to welcome Dr. Schwarzlose here with us for a one-on-one conversation about our new book, Brainscapes. Thank you very much for coming in studio today.
Thank you for having me.
Okay, great. What do you mean by an actual map that's inside of the brain? You can't just like open up someone's head and then point around and look at it. You don't mean that, do you?
Not exactly. So maps that are in the brain are actually part of the brain. They are built into the brain. They're made up of brain cells. But what makes them a map is not that we can open up the skull and just see them, but that they are representing information about our world and in a way that is shaping our experience. But they are laid out in the brain in a spatial configuration that corresponds to our real world experience in our environment. So to give an example, when we have a very large area in the back of the brain that is dedicated to representing visual information. And the layout of this map in the surfaces and tissues of the brain is laid out just like what you see with your eyes. It's actually upside down and right, left, reversed. But there's areas here, will be represented in a particular area in the brain, and something lower will be represented next door. And so what you get is actually like a map of information with neural activity. And to give you a kind of a concrete example of how that works, it was kind of first really mapped out and discovered and really understood through work that was done based on brain damage from a war. And so as the guns got improved and became faster and more efficient, their bullets were fast. They just kind of sliced through the brain as well as other parts of the body, and they would lose part of what they could see. And so what a very clever ophthalmologist discovered as he kind of studied these soldiers who had this brain damage was that if they had damage to a certain part of what turned out to be this map, they would have a spot of blindness in the corresponding part of their visual field, what they could see. And so by seeing this across patients, across the soldier patients, he was able to figure out that this map is laid out according to what you can see, and to figure out exactly how it's laid out. So that's the idea. You can if you puncture this map, or if you stimulate it, you can either create a lack of experience in that part of the visual map, or if you stimulate it with some electricity, you can create the experience of seeing light that isn't actually there. So this map, not only is it kind of amazing to think that maps like this are actually sitting inside of our brain and that they're laid out there, but we are also very actively relying upon them for our conscious experience, such that ultimately what happens in these maps is what we perceive, not even more than what we see with our eyes.
What about touch? How is that actually laid out in our brains?
So there's a map of touch that goes across the top of the brain. There are actually multiple maps of each of our senses. We have multiple maps of touch and multiple maps of vision. But we have what we call primary areas. Those are like the biggest areas that are representing sort of the earliest processing on the outside of our brain to help us represent these sensations. So the main touch map is laid out according to the surfaces of the body. It actually has like your face and your tongue and your mouth down here on the sides. Each represents the opposite half of the body. And then as you go up toward the top of the brain, you go down your body, and you wind up with representing your feet and your toes at the top of your brain. So if you take equipment that can either stimulate the brain with magnetic impulses, or if you were to, as some patients need to do, you can need to have their brain electrically stimulated inside the brain. You can make people feel, by stimulating these parts of the brain, you can make them feel sensations on their body, because this is the map that they use to process those sensations.
I think I remember seeing some video a very long time ago, and they were showing, I guess someone was getting surgery. They had brain surgery, and it's weird that all of these neurons and all that go to your brain, but your brain doesn't actually feel pain. You can't actually feel that. But I remember they touched one part and somebody said strawberries. Like they could taste strawberries. They didn't just see them, they were tasting strawberries. So you're saying the map is kind of laid out along with neurons and nerves, and if you use electricity to touch it, you can actually trigger something somewhere inside of somebody's brain. Is that right?
Yes, absolutely, because the cells in the brain are talking to each other largely through these electrical impulses. And so that information in these impulses is representing together across these many different neurons what we feel and what we know and what we think. And so if you can use electricity to manipulate or to kind of trigger some of those representations that are in our brains.
That's really interesting. And one thing that I have known about, and I think it's been talked about, I think it was with children who were orphans, maybe in Romania, and people were put in orphanages, and they did not have enough touch when they were growing up. It actually changed a lot of the way they even developed and grew up, and the way they thought and cognitive things. And you work mainly with children, is that correct?
We've now learned that actually the brain is doing most of its kind of dramatic organizational development and sort of becomes rather crystallized within about the first year of life. I mean, a lot of it is happening, some of it is happening in the first month or two, very, very early. And so having certain experiences, having sort of certain sensory experiences helps develop and prepare the brain for the next stage of development and the next. And there's sort of this cascade. So major disruptions in experience, such as a child being abandoned or deprived, not having any social or physical contact, those things can create essentially this major lack of development at the early stages, and it deprives them of the opportunity to then build upon that with their later development.
We can bring that into modern times where we've had to be acting in a way that's been very inhuman during this pandemic that we have going on, where you don't actually see people. You're not getting that sort of input, and it's had effects on adults, and it's certainly, my guess would be, it's having some sort of impact on children. I guess the question is kind of in two parts. Was there any past information about this, say during the 1918 pandemic? Was there any sort of thought about that you could go back to and maybe think about? And will there be research going on into that that you might do or others that are in your field might do after this particular pandemic? Because this has to affect the brain somehow.
I love that question. I think that's a wonderful question. I don't know about research after the 1918 flu. I mean, their disruption of their experience was probably different because it was informed or not informed by our current scientific knowledge. I think the question that you're getting at, which is a question that has not been answered, and I think is I've been wondering a lot about myself, is how all of these disruptions to our life in terms of social interaction, and even something as simple as being able to see somebody smile, and as a child seeing, I write about in the book that we kind of develop face recognition. That's something that is very dependent on experience and actually occupies a part of the brain, multiple parts of the brain that help us do that. So certainly that requires practice. we do know at least that children, when they're very young, they usually only see a few faces. They just see a lot of those faces. So we don't, in terms of the most foundational learning, they should still be okay as long as they have a few caregivers that they are getting adequate exposure to. But I definitely think we know a lot less about later in childhood and in adolescence, how exactly face experience shapes face recognition, and I think I think we may learn more, unfortunately, because of this experiment, and it'll be interesting because from now on, whatever studies are done on children or adults are kind of also studies on the effects of COVID, because we're studying people and brains that have all gone through this kind of traumatic and disruptive experience.
I know that you're a specialist in this. You actually helped find or discover a new part of the brain. Is that right?
Yeah, so in my graduate studies, I was working in the lab of Dr. Nancy Kanwisher, who is just a fantastic pioneer of using neuroimaging. And her early work was very impactful in looking at visual processing. So how do we, particularly object recognition, how do we look at something and know what it is? And you'd think that would be really obvious, like if you can see, then you can recognize, but actually it's not. And so there are people who have damage to parts of the brain who can see just fine, but they can't tell you what anything is. They've lost that ability because of a stroke. So she had studied those areas, and I had the fortune of learning from her and working with her. And as we were studying, we were looking at a face selective area. There had been rumors, there had been some findings that there might be some body selectivity for visual body forms. So like, just it could be a hand, it could be your whole body, but in the same area. And so we examined that to try to understand what it was, and found that there were actually two separate neighboring areas. One that specifically, this famous one that is very important for processing faces, so that if you damage this part of the brain, people will have profound problem recognizing faces, even including sometimes their children, their family. And then right next to it, an area that is specialized in representing parts of the body. And that sounds kind of strange, I think, but it's actually, we actually use people's bodies and how they move and they're as part of how we recognize people as well, and we gather our social information and information about identifying people both from faces and bodies. And actually the fact that those two areas were next to each other, in all of the humans I studied, and then other people who have done work in monkeys found that they have the same thing. They've got a body and face area right next to each other. That was what got me going with this curiosity about maps and how information is laid out in the brain. So that was an early and kind of foundational experience for me.
What else in brain research and learning about how the brain maps itself and works came about because of maybe something that's wrong with the brain or through traumatic sort of circumstances? I know you mentioned one thing about maybe people with epilepsy or different seizures.
I actually wind up talking a lot about epilepsy in the book, not as a condition, but because we've wound up learning so much about brain maps as a result of it. And so actually the very first brain map to be discovered in animal or human brains is the primary motor map, which is laid out right next to the touch map on the top of the head. And it's what allows us to engage in actions with our bodies. And it's also laid out according to our body layout. And so a very astute neurologist he had a lot of patients coming in with seizures. And he had noticed that often when they would have seizures, the seizures would travel through their bodies. So they would start somewhere, like, I describe some cases, like one where this finger starts doing this, and then it sort of travels, and now it's the hand, and then it's the arm. So as the seizure, it always begins in one place, and then it would start spreading, and it would always spread in the same way across the body, like in a consistent, replicable pattern. And I think he's pretty brilliant to sit there, and he thought about this, and he thought, what this means is that in the brain, these things that the brain representation of motion of movement is laid out similar to our body, and so he made a lot of really great. Kind of educated guesses at that time based on seeing how seizures moved through patients, and based on occasionally if a patient would die as a result of what was causing the seizures, they could do an autopsy. They would find damage to a particular part of the brain, of that motor cortex, which was starting the illness. So, for example, this would, if it started here with the seizure, the damage, which could be like a tumor or maybe some like trauma that created an abscess, that is the trigger of the seizure, and that's why the problems would begin there. But then that seizure would spread through the map, and as a result, you could see it spreading through the body.
That is interesting, and I wanted to ask you about people who might be amputees, and because a lot of times if you lose a limb through whatever means it happens, you end up with phantom pains, which means maybe just the fact that you are used to touch, assuming you aren't an infant and it can be rewritten, that they say, I still feel it even though my leg is not there or my arm is missing. Is that because that hard wiring is still there and the brain is still trying to figure out what's going on?
Yeah, in essence, yes. So that's the idea that you have representation for a part of your body. You've had it all your life and suddenly you don't have it anymore. Even though it's not there physically, it still has representation in the brain. And the brain it does have these kind of dynamic processes for kind of seeking input, sort of, it does readjust, try to adjust when there's a lack of a normal input, but it can't totally overwrite the organization that it has because it's been crystallized.
You mentioned that most of the brain is kind of set, you say around 1. Is that about right? About 1 year old, or what is it? Well, why don't you tell me?
I want to be careful because it is.
When does it stop being as plastic or what happens?
Yes, because obviously we can continue to learn throughout life. I think one of the things that you kind of, when you have the overview of the brain maps and sort of the developmental processes and periods for the brain, you see that there are sort of different types of learning at different ages. So at the very earliest learning, which the brain begins to develop these maps and the properties of these maps, even in utero, and then within the first months to year of life, they tend to get really very adult-like, and they tend to get fixed. So if there's a major sensory difference in their experience, it can influence the way that those maps are laid out. And if, for example, you have like a child has a stroke, so sometimes infants have strokes around the time of birth. And what's kind of amazing is that, even though these strokes can be incapacitating, they are usually far less incapacitating than the same stroke were it to happen to an adult. And that's because these maps at that age are so malleable, are so capable of kind of change based on the inputs that that babies can effectively kind of reorganize their brains to make the most of what healthy tissue they have left. So that kind of process happens very, very early. Part of the challenge is that we do lack this plasticity as adults that we have as children. Our brains are much more fixed. And so once everything has been, the different parts of the brain are highly specialized, and that has crystallized, and their kind of functions are more or less set. If you take out part of the brain, take out one of these areas, much less many of these areas, there are still opportunities to recover, but it is just a lot harder because the rest of the brain is already doing something. And so we just don't have the extra, we can't replace that part of the brain that was missing and that function that it fulfilled. So what actually often kind of the focus is on is rather finding ways to sort of make more with what remains, finding new strategies to accomplish your goals, like getting yourself dressed in the morning if you're having, motor problems. It's kind of practical, and using what resources you do have neurally, the areas that you have intact, to help you accomplish the things that you're no longer able to do.
I've taught English abroad, and one of the things, especially here in the United States, many people only grew up speaking English or one language, and they don't speak anything else. And kind of a natural thing a lot of people reflexively say is, well, only babies can learn languages really quickly. And I've found that that is nowhere near as true as we think. I think a lot of other things get put in front of that. Is that borne out by the science? Because what I have found is that if you put people in the right environment, they're in a good class, they have some other sort of motivation, they can pick up on the language. No, they're not going to learn it like a 1-year-old, but you can still learn it, but it might be more difficult because of all the other adult things that you have going on. Is that borne out by the science that with language, and I guess language probably has a part or a space in the brain as well, and language acquisition and all of that to acquire a different one?
Within the first year of life, infants go from being able to equally recognize any distinction between two different speech sounds in any language spoken on Earth to being unable to hear the difference between speech sounds that are not separated in their language. So kind of we take speech sounds, all these mouth sounds that we make, and different languages divvy them up as what is a different sound versus the same sound. Because actually there's a lot of variability in how all of us speak. And so infants, when they're first born, they can hear any distinction. And then by about 6 months, they're already losing the capacity. Behaviorally, we've tested this. They lose the capacity to hear distinctions in languages other than what they've been hearing. And this is part of why sometimes you learn new language. This doesn't sound different. It sounds like the same word you're talking to me, but you say they're two different words. And that can be overcome with attention and with effort, and we can kind of learn to hear phonemic distinctions we had lost the ability to hear. We can learn new words and learn new ways of speaking new sounds. It's just a lot harder. It's very, very rare to reach a level of fluency of a native. So a lot of times, when what comes out of the literature from neuroscience and psychology is I think highlighting the fact that as an adult you can't just speak like a native, right? As a child could. You put a child in, take them to another country for a year and they're good to go. So that distinction is a real one and a valid one. But I think as you point out, and I think as we should keep in mind, the brain is still capable of a great deal of learning. And just because we can't reach whatever kind of bar or standard of perfection might be set out by a particular kind of study group or approach, that doesn't mean that we can't do it. And I think the fact that you can learn a new language and go about and actually have meaningful conversations with natives in other areas, and they can understand you and you can understand them, and say that is a testament to how continued learning can benefit us.
So does everybody have their own brain fingerprint, if you will, for terrible language? And your brain is not your finger, but do you have your own ID, kind of like DNA, and does your brain light up in a specific way that's different to everybody else's?
In some ways, our brains are very similar to not just, each other's, yours and mine, but even to, a whale's and a bird's, less a bird's, but a dog's. So it's kind of remarkable the similarities that we have across individuals and even across species. But at the same time, when you zoom in, and in certain areas that are kind of a little more free-flowing than these maps that I'm describing, you absolutely see unique differences. So there's an emerging line of work that's done neuroimaging with individuals where you get a lot of information from each person, and then when you compare across them, you find that there are these small but systematic differences that could be, contributing to how they individually, think and perceive the world. And so I think that we can both say that there's something very kind of unifying and universal in our brain structures, and the gross structure is highly similar across all people. But when you get close in, you also can see the ways in which we are very unique, and that can be shaped both by our genes, and our environment and our experiences through life. So that at the end of the day, all the things that make us unique as people, they're encoded somehow in our structure of our brains, and that's part of how that happens.
So why did you write this book? You're in academia, that's what you do, and writing a book or writing papers and even the review that you worked for, writing for so long and being the editor for so long, what made you want to do a book for the general population?
It's a great question. I think when I fell in love with brain maps, and the more that I learned about them and from the scientific literature, building off of that face and body discovery, the more I explored them, the more I was really struck by the fact that there wasn't any accessible account of them that kind of really described across the different sensory modalities in a way that everybody could understand. And I think that the reason that there wasn't that existing kind of book out there is because these can be difficult concepts. It has to do with kind of, you have to sort of mind bending, and so but I thought, we should not allow that to keep us from conveying that information to the community and the general audience, especially because it touches on important social issues like child care and child well-being, and how we should be spending our dollars to support child development, and it touches on neurotechnology and how we should be thinking about what technology we want to engage with in terms of our brains, and also how we might want to be regulating the technologies that are out there and how our data may be used. But if you don't understand the basic principles of these maps, then all of those implications become very, very hard to work through. So I think it's like a tool that people, that people deserve to have, that especially the public, because neuroscientists know about these maps, and we've known about them some of them for 150 years. And the fact that most people in the general public don't know about them, and therefore are not going to be able to engage in a dialogue on these important social issues, that's a problem.
And do you have another book in you? Is there something else that you might like to spread to the masses for the general population about the brain or other areas that you're expert in?
I have a lot of focus to do on my research. So I'm actually not planning another book anytime soon. But I am hopeful that I can continue to have a dialogue with the general public and share the discoveries from the scientific community in different ways, and maybe someday. But for now, definitely excited to continue and push forward with my own research.
And what's your research in now? What are you focusing on now, if you can talk about it?
Yes, I can talk about it. So I'm actually the process of writing this book helped really focus my interest not just in development, but on sensory experience in children, and particularly children who then have different psychopathologies. For example, autism, OCD, attention deficit disorder, Tourette's syndrome. So I have been really focusing my attention on trying to better understand neurally what is happening in the brains of children who are struggling with sensory overresponsivity.
Okay. Well, Rebecca Schwarzlose, thank you very much for coming in with us today and talking about your new book, Brainscapes, and how everything is mapped throughout our brains, and hopefully the general population can use this to our advantage in the future. And it was certainly great, me learning a lot more about the brain than I knew before. Thank you very much.
Thank you so much.